Hello? Perfect. So wonderful. Thank you very much for the applause. I am a researcher and an implementer of these sort of distributed deep learning libraries inside of Spark. And so this talk is going to be about new algorithms that we've developed in Spark. So specifically about convolutional neural networks and doing it at big data scale inside of MLlib. So just a little bit about me. I'm basically an engineer at the Spark Technology Center, and I contribute to MLlib. So MLlib is Spark's deep learning library, and I've been working on scalable deep learning inside of it. Before I was at the Spark Technology Center, I studied applied math to CS and econ at Harvard. So this audience is basically very machine learning focused, and so I guess I want to talk a little bit about Apache Spark, why it's valuable, why so many people are using it for ETL, and why it'll be useful to integrate machine learning with the rest of your analytics loads. So about Spark, so basically it's for doing large-scale data processing. In general, when people are doing large-scale data processing, they'll have their data in HDFS, so in Hadoop, and Hadoop has this default computation paradigm of MapReduce. So Spark created this innovation where instead of basically doing iterations by writing to disk and reading from disk over and over and over again. So in the case of machine learning algorithms like logistic regression and like neural networks, where you're basically computing a gradient over and over again, you'd have these extraordinarily slow workloads. Spark basically allows you to do these computations in memory across a large compute cluster. And so for these iterated jobs, you have like 10 to 100 times speedups for things that are reading and writing a disk in HDFS. There's also this improved usability. So the API that most data scientists want to use in Python and PySpark has been made available. And that was actually a real difficulty in doing data science on top of extraordinarily large data sets. There are also Java and Scala APIs, so sort of like classic analytics workloads, and people who are comfortable with those tools are basically using them. And basically MLlib is implemented in Scala, so a lot of the code that we're writing is this like distributed Scala database. So this is a little bit about MLlib. So MLlib is Spark's machine learning library. It's basically a packet of tools, very basic tools for doing large-scale data analytics. And so we have alternating least squares. So if you're trying to create a recommendation engine, you can use that for collaborative filtering. If you're basically trying to do linear or logistic regression, you have those options. There are decision trees, naive Bayes, and SVMs. But when I joined the SDC, one of the major things that was missing was basically being able to do large-scale deep learning with MLlib. And so this is about adding one major algorithm that's gotten state-of-the-art results on lots and lots of important tasks. Advantages to MLlib include it being integrated into Spark. So basically, when you're doing ETL, Spark is extraordinarily efficient. You also often want to do machine learning on top of that. And so you'll have a single integrated environment in which to do all of your data analytics. It's like extremely scalable and has like a nice body of APIs as well. As far as deep learning in MLlib is concerned, advantages include basically the benefit from extremely large data sets. So for example, if you have a huge number of images, so I guess like Flickr had this data set with hundreds of millions of images, storing that in HDFS and doing the compute with Spark allows you to do extraordinarily large data analysis. And for deep learning, this makes a lot of sense because you have these extremely large models, and in order to get sufficiently low variance, you're going to want to add as much data as possible. And the accuracy will scale with the data much more efficiently than with other algorithms. Spark makes this large-scale data analysis really easy because it has this RDD, resilient distributed data set, which will distribute your data across the cluster efficiently. And by doing it in MLlib, the compute will be local to the data. So basically, you won't have to move your data, this extraordinarily large data set, from this distributed Hadoop cluster to an entirely different node or set of nodes in order to do deep learning on them. Everything's integrated into Spark's pipelines, which is also extremely convenient. So here's a few links to this package for doing deep learning. You'll see this again later in the talk. But basically, the structure of this talk will look at first framing deep learning. So I guess from the perspective of a researcher and from a data scientist, how do you think about improving these models, and how do you think about in what contexts you should apply, in this case, convolutional neural networks, but in general, different machine learning algorithms. Second, I'll walk you through this MLlib-based deep learning API. You'll actually be pretty familiar with it. So I guess, does anyone here use Keras? Yeah. So I guess this API is the Scala analog of Keras, and so you'll be able to do import-export from that library. So I guess anything that allows you to do import-export into Keras. But you'll also be really familiar with the API to begin with. So you'll see that in a little bit. And after that, I guess I want to talk about optimization. So basically, we've implemented a lot of modern optimizers, which lead to dramatic improvements in both the performance of the algorithm, so I guess like the speed at which you get to convergence, but also the overall accuracy. And you can see the stability of the training and some of the visualizations that I have of these optimization algorithms. Then we'll look at performance. So I guess a lot of that is like, how is it being optimized? So we have this compute cluster, and there are a number of ways that you can basically take your gradients across the cluster and average them and combine them, whether it's like synchronous or asynchronous. And so we'll look at Spark's model for that. Finally, look at future work for this package, and then jump into how you'll do deep learning in Spark in general. So there's this basically history of projects that are trying to make deep learning on Spark work, and I want to show you the upsides and downsides of taking particular angles of attack on that. Finally, we'll look at deep learning outside of Spark if we have time and finish up. So first on framing convolutional neural nets. I want to start talking about structural assumptions, automated feature engineering, and learning representations, because from the perspective of a data scientist, you want to know when you should use what tools, and this is extremely important for that. So first on location invariance. Basically, convolution has this really valuable property of basically assuming that anything that is not local is zeroed out. And so what that does in the context of image processing is say you'll have an image, say of an audience, and that image will basically have a number of filters that are dragged across it. And the locality allows you to basically say that basically pixels that are close to one another are going to have interactions with one another. And then at the next step in the hierarchy, you will combine sets of pixels that had interactions with one another locally and start to learn this feature hierarchy. And so you can see in this image that you're only looking at a small subset of the data. And that's actually a really strong prior, that the only interactions that you care about in your data are going to be local interactions. And that's actually extremely efficient because in general with networks, if you have a fully connected network, you're going to be assuming that there's equal weight between the prior on the interactions between your features. So every feature will be interacted with every other feature. And in this context, assuming this particular structure lets us search function space for functions that are going to take advantage of that localized structure. And so in the context of image processing or natural language processing or audio processing, this structural assumption is extremely valuable. The second is learning a hierarchy of abstractions. And so basically at the low level in image processing, you'll have pixels and you'll have curves. And once you move up the hierarchy, you'll basically recombine those pixels and curves into higher level objects, like shapes. And those shapes will recombine into the shape of a face or the shape of an eye if you're doing facial recognition. If you're on ImageNet, like color ratio will also play a part. But basically, this set of levels of abstraction lets you do a number of things. So one is that you will have this high-level representation that can be ported to another context. So you'll basically be able to do transfer at different levels of abstraction in the hierarchy, which means that if you, say, train a neural network on ImageNet, you can take the lower-level representation, which is going to be similar to the lower-level representation in some other data set, and then do very efficient transfer learning because you're taking advantage of that lower-level structure that exists in data sets that you'll see in image processing, but also in audio processing and natural language. This is well explicated in this sort of Zieler-Fergus paper where you can actually get visualizations of the filter maps by basically doing what's called deconvolution. So you'll try to go back to the original image and see what types of object activate your filters. And in this case, the lowest layer, you actually see extremely simple, colorations and these lines or edges, and it basically is a reasonable model for almost every image data set that you'll see. So those feature maps transfer very efficiently to other data sets. Basically, the features that are being learned here are coming directly from the data. And so it's extremely powerful in that whatever it is that you're optimizing for, you will learn a representation that is most likely to make that prediction. So your gradients are basically trying to say, update these filter maps so that I can classify, the body of images that I'm looking at most accurately. This also makes transfer learning feasible. So these lower level image representations can be transferred to another data set and speed up training dramatically. And in general, there's also transfer like internally inside the data set. And we can see that with this sort of like compositional structure that we learn. So here you're thinking about this hierarchy of abstraction. So there are a lot of ways that you can get a hierarchy. Like one way to get a hierarchy is, say, like recursively. So you'll stop at the top of the hierarchy, and you'll cut the top version into subparts, and you'll cut the subparts into subparts, and you'll end up with this like top-down structure. But composition has this bottom-up structure to it. So you'll have like a number of low-level pieces, and you'll be recombining those pieces with one another. And in those recombinations, you'll basically have extraordinary expressive power. But in a lot of cases, you'll actually capture important structure in the data. So we already talked about how image structure has this nice pixels to edges to shapes to parts to objects, like sort of hierarchical structure. But that also occurs in language. So at the character level, you'll sort of recombine characters to like create subparts of words. You'll create those subparts to create full words. Those words can be combined into short phrases, and those phrases will be combined into sentences. And as far as like the meaning of the content of the language goes, you can have a word be a concept, or you can have a phrase be a concept, and the sentence will usually be some composition of sets of concepts. But basically, there's a hierarchical structure in terms of the literal way that the English language is laid out, but also in terms of the way that it's laid out conceptually. And those recombinations allow you to basically interact with the data at the level of abstraction that's optimal for making whatever prediction it is that you care about. But it also lets you more efficiently transfer from information that you have from one set of data points to another set of data points, because there's more generality at some levels than others. So basically, as you move up the abstraction hierarchy, you'll get more and more generality. So I guess in the case of images, you're basically like finding a compressed version of the image that you can feed to a linear classifier. So there's this phonemes to words like structural assumption that you also see in audio processing. Basically, when you're looking at this audio stream, you can imagine thinking about it at the word level and like that being the level that you care about. So you're trying to say, figure out what words people are saying inside of the audio stream. But there's basically sets of frequencies that are composed into the word. And so our language has, like, at a character level, this sort of makes sense that you're going to, for each character, say something that sounds similar. And those are things that you'd like to transfer across different data points. And it's by recombining these small sets of characters that you end up with phonemes, and those phonemes get recombined into different words. And so this compositional structural assumption is actually very useful for a number of categories of data set. And so in those contexts, we've actually been able to improve on the state of the art dramatically using deep learning. And that's extremely important. So what comes out of learning with these different types of structure is a number of amazing applications. So we've basically gotten to a point where doing object recognition in a lot of cases is easier with a network than having a human look at the data. That object recognition and localization and image segmentation has been rolled out in umpteen examples. You saw the drone example earlier today. About autonomous cars and how they've been using all of these tools. They also work really well for image restoration. So one thing you can do is take the most likely pixels that you would have if you increased the grain of the image, or if you basically we're going say from 480 to 720. It's okay, what's the most likely sets of pixels, and can we interpolate? So you can use it for image restoration, for music recommendation. So if you're Pandora, you'll ask, okay, here's this set of audio streams. One thing we can do is attach high-level concepts to each song and say, okay, well, you like hard rock, and so we're going to try to give you more things like that. But you can also, at a lower level, say, here are a number of songs in a genre, and what are the lower-level features that are actually predictors of our genre, and how is our intuition for this song belonging to this genre being constructed? And there's this sense that you can get a much more granular representation of what it is that people like about music by looking at lower levels in the hierarchy and sets of recombinations in that hierarchy. And so you can use convnets for music recommendation. It's being done at Spotify and at Pandora. RNNs have also gotten state-of-the-art in a lot of these natural language tasks. And in parts, it's because you can do sequence learning with RNNs. And in general, machine learning models will have this fixed input space, which really limits the type of task that you can point them at. But RNNs have been extremely useful for doing all of the number of language tasks, including speech recognition, QA, machine translation, et cetera, et cetera. Final set of assumptions, so basically weight sharing is extremely important. So it allows you to basically take a filter map in an image and try to apply it to every single set of features. And it comes out of the homogeneity of, say, an image or an audio stream. So I guess every single set of features that you have is the same. So it's either all pixel values or all frequencies. And that lets you share information across the image or across the audio stream. It's really valuable. But there's also this sort of like combinatorial flexibility that you get. So in general, in machine learning, you want to be able to represent the function that is like closest to the data generating distribution function. So the data has some structure, and you want that function to represent that structure. And this gives you lots of flexibility in searching for that function in space. Basically, when you do this sort of compositionality, all of the different recombinations of your features are possible outputs for your network. And that combinatorial structure lets you combat the curse of dimensionality. So you can also do automated feature engineering. So basically, the feature hierarchy in general is too complex to engineer. If you try to have your data scientist take a set of images and have them figure out which sets of pixel combinations are going to give you some higher level feature and then like take those higher level features and try to recombine them, the data scientist isn't going to be able to accomplish the task. Basically, the space is extraordinarily high dimensional, and the grain at which the human mind interacts with the data is not appropriate for doing that category of feature engineering. So you can automate this for feature hierarchies, and this works really well for compositional structure. In general, you run into an overfitting problem if you're not doing automated feature engineering over compositional structure, and so there's a sense that like DL may be a panacea, but it seems like for contexts where the structure of the algorithm matches the structure of the data, we're doing extraordinarily well. And in other contexts, we have to employ massive amounts of regularization, like dropout or L2 regularization, trying to deal with the fact that our function is extremely expressive and is just going to overfit whatever data it's looking at with a set of assumptions that's different from the structure of the data. So it's not like a general automated feature engineering engine. It's automated feature engineering, but for compositional structure. So this is a great image from Crystal Law. So the representation that gets learned is the one that ideally separates the data. In this case, you have the sort of blue and red classes. Here, they're not linearly separable, but we'll find a representation that will make them linearly separable. And that's by doing nonlinear combinations of the feature input. So I wanted to introduce all of these structural assumptions to MLlib. And this is an example of the API that we're basically making accessible, and it's very much like Keras. So it's higher level enough that a data scientist can be efficient about putting their architecture together, but low level enough that you can express whatever type of algorithm that you want. So I guess there was an initial MLlib deep learning API that wasn't nearly this expressive, and so it was hard to introduce new activation functions and new layer types. But we've opened up the API, and so now you can see that, much like Keras, you'll create a sequential, and you'll add convolution or max pooling layer types to that sequential. You can add activations. Linear ReLU activations are on site here. The dense activation and a softmax layer at the end. And basically, we have an atom optimizer, and we'll fit our model. And the value of an API like this is that basically you can port code that you have in a different context to this MLlib API very efficiently. If you're using like PySpark, Python side API, it's like almost direct. And if you're converting it into Scala, there's this nice one-to-one correspondence between the types of object that you're putting together. So the modularity that you have also basically enables you to do a number of things. So you can do feed-forward networks by, say, adding a dense layer, but you can also replicate logistic regression. So logistic regression is basically this last layer, this softmax layer that we have on top of our network. But we don't actually have to include any intermediate layers. And so you can, with an API like this, just flexibly create logistic regression by having a dense layer and an activation immediately after it, and then optimize it with Atom and apply whatever regularization techniques it is that you want. So this is basically an example of how much you can improve training using momentum. So momentum basically cancels noise in the gradient. So we added this optimizer that will look at your previous sets of gradients and will average them together. And so there's noise in every single gradient, but that noise isn't going to be consistently in the exact same direction. And so by averaging together previous gradients, you can cancel the noise and increase your speed in the direction that all of the gradients basically concur that you should be going in. This is another optimizer that we added. It's called RMS prop. And what it does is it basically automatically tunes the learning rate of every single parameter in your network. And the heuristic it uses for that auto-tuning is taking basically parts of the network that were being trained too quickly in the past and slowing them down, and taking things that were being updated very slowly and speeding them up. And so that makes it possible to use the entire network in terms of like sets of gradient updates that you're getting. And so you get a much more balanced optimization process. In Spark, we have this distributed optimization paradigm. So we basically compute gradients on each worker, and those workers will basically push their gradients back, and on the master, we'll average them. You can see performance numbers here. I'm going to finish up real quick, but basically this access page will give you a link to this Spark DL library. It's also in Spark packages, and so it's accessible here. Also, the slides will be provided. We have some future works. We're working on GPU acceleration, the Python API, and Keras integration. And that's everything. Thanks so much.